So we started this last time. Okay, started talking to graphs. So how do we, which equation makes that happen? So we know it's some kind of x squared thing. So it's not that one, right? It's some kind of x squared. We know that just plain x squared, starts in the middle. All the graphs. Remember the basic six that you're going to want to put in 3x5 cards. So that's one of the basic six. It's the U shape. They all start at the origin, okay? But what makes the thing turn upside down and go up like that? That's the question. Well, couple of things I would suggest if you get this kind of question on an exam. I can tell you what makes things happen, but probably one of the safest things for you to do is just make a table. So for each of these. So could it be that one? Well, let's try. What if I made an XY table? If I put in x0, would that work? What would I get? 0 squared minus 7. That would be minus 7. That would be the point over 0 down 7. Is that right? Does this graph have the point over? That'd be down here. No, it doesn't go through the point over 0 down 7. That ain't it. Good so far? So could it be B or C? So let's try B. So XY table again. Just put in 0 because that's easy. Could it be like that? Well, that'd be negative 0 minus 7 squared. That's negative 7 squared. That's negative 49. Over 0 down 49? That'd be way down here. No, we know the answer now, huh? But let's see it's true by the table, and then I'll talk to you about what those things do. So, whoops, kind of run out of room here. I'm bringing it over here. So, xy. So y equals minus x squared plus 7. So put in 0, and that'd be minus 0 squared plus 7. That's just 7. Over 0 up 7. Yeah, that looks right. Over 0 up 7. And then if you go like 1, it's going to be minus 1 squared plus 7. It'll come down a little bit, only be at 6. Over 1, it's coming down. Yeah, it's right, huh? It's doing the right thing, isn't it? That is the right equation. Now, why? Why is that? Let me talk to you. So I'm going to try to appeal to you from two vantage points, like what the things do and then the table work. So basically this negative multiplier flips the thing upside down, and the plus 7 moves it up 7. So this is flip upside down. So the negative, which is really like a negative 1, timesing it there, flips it upside down, and the plus 7 moves it up 7. Let's talk a little bit more about what these kind of things do. Let me start with. Do you remember the y equals the square root of x? What does that graph look like? Remember that's the firework. Starts here, shoots off to the right like that. Firework graph. Okay, so that's a nice, easy one to move around. Let me just show you what happens when we start moving that thing around. If I put a negative right there, really, let's just say a negative 1, which is it's the same thing as just a negative. So if I put a negative right there. So I talked to you briefly, didn't I, about x effectors and y effectors. Whether a number or a negative sign, same thing, affects something vertically or horizontally. So what did we say about that? I talked about, didn't I make a compassion example? That enter into their little world. So this guy is going to be a y effect. Versus if I come down here, let me change the color and come down here. If I do this, that guy will be an x effect. Because he entered in, to x's little world there. Everybody see the difference? So what does that mean graphically? Well, that means graphically, this is a y. This negative is a y, so it'll have a y. It'll make it throw down, like vertical kind of thing, right? Whereas the blue one, the negative flip things, right? Negative multipliers flip things. This could be x. This will make it flip left. Instead of down, it'll go left. Let me draw that a little better. Everybody see that? So let's start with that. So the first thing to notice about items put into equations is whether they have a right-left kind of effect or an up-down kind of effect. Right-left is x, up-down is y, and that's all about whether they get into x's little world. And what I mean by x's little world, all these functions like x squared, it would have to be in there with the x squared. or, absolute value of x. It would have to be in there with absolute value of x, and on you go. So whatever is happening to x in the equation, if the negative sign or the number or whatever enters into that absolute value or x squared or square root or whatever, then it's an x it's going to have a right-left kind of effect on the picture, on the graph. If not, if it's outside like that, it'll have an up-down kind of effect. That would make the v go down to have this. Because that negative there is a y effect. Whereas if you put it in there, it would just make the v turn sideways, which makes it look like nothing happened. Turn a v sideways, nothing happens. Right? See the difference? And we know that, huh? We know a negative inside of an absolute value does nothing. And that's what the equation rules tell, the graph rules tell us too.
So
Question?
to get to the third quadrant, it'll be a negative?
Both negative, huh?
Yeah. Negative,
yeah, exactly.
Negative, so.
You could put both negative in the x and the y, and that, yeah, you're right. I can show that. Yeah, so if we had y equals negative root of negative x, that would flip it upside down and left. So it would go that way, wouldn't it? Because it's got both an x and a y effector. Good on that so far? Okay, so if you got that down, I'm going to go to fresh screen. Now, that's part of the story. Let's go back to, let's talk about y equals square root of x again. Now, let's talk about numbers added and subtracted. So let's talk about, here, let's do this. Let's talk about x and like add 2 or whatever. Versus, over here, let's talk about add 2 inside the root. See the difference now? In the black one, the 2 is outside of the root. He's not in x's world. The red one is. So this one, is this 2 here, is this an x effector or a y effector?
Y.
This is a y effector. It's going to have an up-down kind of result because it's not in x's world. Whereas this one over here is going to have a right-left kind of effect because it's in x's little world, right? We all getting the hang of that? Now, what does adding and subtracting numbers do? Adding, subtracting, instead of multiplying. Everybody seen the difference? Back here, these were all minus 1s multiplied, weren't they? Timesed. Nothing was added here. These were all timesed, weren't they? Right? They were right next to the x or right next to the root. There was no adding, subtracting. All those were minus 1 multiplied. And multiplied minus 1 flips you. Or minus any number. Do a minus 2, that'll flip you too. You multiply by negative anything, it flips it either vertically or horizontally, depending on whether it's an x or a y effect. Now I'm talking about adding, subtracting. That's going to be different. So when you add or subtract, it moves the graph. It doesn't flip it, it doesn't stretch it or compress it. It moves it. Multiplying, dividing, stretch and compress, adding, subtracting, move the graph. So it's going to move it. So what then? What is that plus 2 going to do? It's going to go up 2, huh? So you just take the normal square root of x graph and you just say, instead of the origin, go up 2 and do your same old thing. That makes sense? It's still going to shoot off to the right because nothing else hasn't been flipped or anything. We'll put all these together in a minute, but for now, that's just a up 2. Whereas the red one, now the red one, it's not going to be up 2. What's that 2 going to do? Trick question. You remember from yesterday? You guys never forget anything I say, right?
Go to the left.
Good. You remember it's opposite. Good. Some remember. X always has, because normally you think plus 2 right 2. That'd be the natural thing to think. But X is always opposite. Everything's opposite for X. Y is normal. X is opposite. So it's actually left 2. It's actually left 2. So it'll take it left. Instead of being at the origin, it'll go left 2. Whoops. And it doesn't shoot to the left. That was wrong. It still shoots the same direction. Nothing changes with the fact that it shoots off to the right. It just has moved its starting point. You've just moved the firework left 2 spots. Does that make sense?
Is that because it's in vertex form?
It's because, there's a couple reasons you could say it. You could say because the number is right next to the x, but for the y thing, they're on the opposite side of y. That's really what it is. See, if you moved this 2 over to be next to y, it'd be y minus 2, and then it would be opposite for y also. So really, it's always opposite when you're right next to your letter, and same when you're on the other side. That's what it is. There's no real magical difference between x and y. It's just the way we write the equations. So anyway, I don't want to bug you with all that for now. but that's the reason. So just remember, because we're always going to write the equations like this for now, we will change things up later, a month from now, and I'll say, hey, remember that was just for then, but here's really the deeper truth. But I'll unveil it step at a time here. For now, x will always be the opposite because we're always going to write the numbers right next to x. And y will always be the same because we're always going to have y numbers on the other side of the equal sign from y. So that'll work for you for now. So that's the case. So that'd be left 2. So we good there. So now, what if we put a multiplier? What if I put 2 square root of x, and then let's go over here and go square root of 2x. So this 2, is that an x effector or a y effector? So y effect. But now this is times. That's not a 2 added. This one also is times, and you know this one's going to be an x effect over here, because it's in there with x, okay? Now, what does multiplying dividing do? That's the question. Multiplying stretches and dividing compresses. So it doesn't move it, right? Adding, so back over here, adding, subtracting moves a graph. Multiplying, dividing, I'll just put div. Multiplying, dividing stretches or compresses, except for y does the opposite, even here. Not y, I'm sorry, x. X does the opposite. So he's got to remember, x always does the opposite. So this is what we would normally expect. So right here, let's do this first graph. So this 2 is going to have a y effect. It's going to stretch it. So it's going to just go up twice as high. It's going to go up twice as fast. Let me say it that way. It'll go up, because it goes up infinitely high eventually. It just goes up twice as fast. Does that make sense? The y has been stretched up times 2 high. Whereas on this one over here, this is going to have a 2 times x effect, but we would normally say it's going to stretch it twice as much on the x, but in reality, actually, what happens? X is opposite. So it's not going to stretch it twice as wide, it's going to compress it. So it's going to compress it. I don't know if that looks like. Yeah, it's hard to tell. A lot of it's from the table, is where you get the actual values, but it compressed it 2 times as much. Yeah, a lot of times that's hard to tell, and you just need to use table values. They'll give you a couple values. But it compressed it horizontally. Didn't move the starting point. Both these are still starting at the origin. Isn't like the last one where we moved the starting points, huh? Everybody see that? So the difference between moving a graph versus stretching and compressing, and then the negative multipliers, back here, where were they? They flip the graph, all these negative multipliers. All right, that's really the story. So let's our test. All right, so that's V shape, absolute value. So let me just get rid of this option. It's not that. I'm not going to put dumb multiple choice options like that on the real test. They'll all be absolute value. So it's not that one. So what can you tell now? No, we can make tables. And if it was my test, I would make a table. But before we do, can you just tell right now that thing's been flipped upside down? Let's just take the basic equation and say, okay, what would I do to flip it upside down? Where would I put the negative? In front, like that, right? Because that's a vertical. That's a y effect, an upside down, not a right left. Okay, so which one of these have negatives in the front? Well, that one and that one. So it's one of those two, isn't it? Okay, now, it's been moved to the left 1. Left 1. It's not starting at the origin like normal. It's been moved to the left 1. What moves the graph to the left 1?
It's inside the
X plus 1 in there. Opposite. So it's minus absolute value of x plus 1. So it's this one. Now, what's wrong with that one? What's wrong with that plus 1 there?
That's indicating to go up.
That's an up one. Because that's outside. That's a y effector. So we got. Now, again, if it was my test and I had a minute, I would make sure I would just do a couple quick points. I go, really, let me check. This point, for example, I'd say, okay, this should be back 1 up 0. Right? Doesn't that look like back 1 up 0? I would say, is that true? If I put in back 1, is that really going to work for that one I think is the answer? And I'd go, let me see. Plug in the negative 1 plus 1. Yeah, that's 0. Yeah, it seems like it's working. Maybe do one more point. 0 or something, I don't know. And get minus 0 plus 1, that'd be minus 1 over 0 down 1, is that right? Yeah, over 0 down 1, yeah. Oops, that looks right, it's about right there. Yeah, looks like it's right. You can double check with some table work. language, which I think you know what to do, but the language might throw you, so let me help you with that. So it says, take y equals x cubed plus 4, but reflect about the y-axis. That's the weird kind of talk. What do they mean? Well, here's the y-axis, okay? Let me, I'm racing ahead of you. You get what it's saying there? So it's y equals x cubed plus 4. And they want me to take that equation and do something to the equation that will cause the graph to reflect about the y-axis. Now, what do they mean, reflect about the y-axis? Well, if the y-axis is your mirror and you reflect, say, from here to there or vice versa, right? You're reflecting across. It's a horizontal flip. It's a sideways. Sideways, or in other words, x. That's what's tricky. They say y-axis, but when you reflect across the y-axis, you did an x flip, really. I mean, the way we usually say it. It's a sideways flip, isn't it? It's an x effect, really. That's the trick. Watch the language, right? When they say flip across the y-axis, that's a sideways flip, so it's an x effect, really. And if they said flip about the x-axis, that would be a y effect, a y flip, really, right? So watch out for that. So, okay, so they're really saying, take this thing, take this equation, and make an x flip. Really what they're saying. So what do you got to do? What's going to make an x flip? You got to put the negative in there with x, don't you? That's what makes the flip. Everybody see that? The negative in there with x. That's the answer they want. All right, good? All right, I'll keep it tricky. So, but valuable. Y equals square root of x. Okay, horizontal stretch. Horizontal, that means horizontal sideways, right? X stretch, factor, factor of 7. Like 7 times is wide, right? So take it, stretch it horizontally, 7 times as wide. So take that equation and make that happen. Let me give you 10 seconds. So let's take it in pieces. Is that going to be an add, subtract kind of thing or a multiply, divide kind of thing? Multiply, divide, right? Add, subtract moves it. Multiply, divide stretches and compresses, okay? So first off, we're thinking I'm going to multiply or divide by 7. Right. Okay, outside the root or in the root? Inside. Inside, because it's an x thing. It's got to be in there. So I'm going to multiply or divide by 7 inside the root. Now, does x do the same as we would expect or opposite? X does opposite. X does opposite. So stretching, we normally think multiply, but x, if it was y, we would. But it's x, which does opposite. So what am I going to do? Divide by 7. Did you catch that? Right? X does opposite. You always got to be watching x. He's opposite. Good? Let's keep moving. If they had said y, vertically stretch, then I would have taken the equation. Whoops, kind of getting scribbly there. If it had been a y thing, I would have said 7 multiplied in the front. Because y just does normal, so stretch is multiply, and it would be in the front. Right? You with me? But x does opposite, and it's inside the root, so it's divide inside. So y equals y squared of x. Okay, let's do it one part at a time. So down 3. So take that equation and move her down 3. So down 3 is a y thing. So the action is subtract 3 outside of the root. It's not inside the root, right? Inside the root would be right, left kind of stuff. Right, that's outside the root, so it's a y effect. Right, down 3. And y is normal. Negative is down, positive is up. Good so far? That's step 1. Stop me if you want to talk about it. Step 2, now, keep going. We're going to build piece by piece. Now reflect the thing about the x-axis. Now take the equation and reflect it. Take this equation and reflect it about the x-axis. Remember what that means? Now, if you have the x-axis, you reflect from here down to there or vice versa. It's a vertical flip, isn't it? Reflecting about the x-axis is really a y effect. It's a vertical flip. So this is a vertical flip, a vertical or y flip. Right? So take that equation and make a vertical or y flip. This is tricky. What do you do to make a vertical flip on that equation? Well, yeah, how do I say this? Yeah, let me do it this way. This would be the best. Is this true? Yeah, I'm trying to say it in the easiest way. Replace y with negative y. How about that? Yeah, let's do that first. This will make it easier. So take that y and replace it with negative y. So far, so good? And then you got to turn that back into normal y. So multiply both sides by negative 1. Which means the negative goes all the way through. That's the part I want you to realize. It doesn't just go in the front, it goes all the way.
How can we keep the 3?
How come I keep? Because I'm building. Right? Find the function that is finally graphed.
Oh.
So I'm building piece by piece. I'm not going back to the beginning every time. I'm doing whatever I do the first step and then build upon that to the second and the third. Right? So, hold on for a minute. So everybody see that. I know this tricks a lot of people right here. A lot of people do this. Probably most of you did. Probably most of you took this equation right here and you just threw a negative in the front of the root x, huh? Right? Yeah, that's not right. And the reason it's not right is because you have to do the negative on all of y. And what is all of y equal? The whole right side, not just the front part. So either way, if this replace y thing is weird for you, then you could just think to yourself, the whole thing, just negative, positive. You got to change the whole thing. Or you could say, put a negative 1 in front of the whole thing and then distribute it. That's right. That's true. But you know what? I am trying to make things consistent for you. So if you want one consistent rule that'll always work, that's how I like things, then you can always think whether they do x or whether they do y consistently, if you just replace the x or the y with the negative x or negative y and then work it out, it'll always be right. It'll always be right. So I like that. I like just something that's consistent. Because watch our next step. Next step now, step 3, they're going to flip it the other way, right? So remember where we're at. Right now we have, well, what do we have? Right now we have y equal negative root x plus 3, right? That's where we're at right now. Now, step 3, reflect about the y-axis, which that's, the y-axis, it's a sideways flip. When you flip about the y-axis, that's an x flip, okay? Now, what do I do with this equation to do an x flip? Replace x with negative x. So notice it becomes the negative still in the front, negative x in there. But you don't mess with the plus 3. Why not? Because you're replacing just x. This is just an x flip. Just x with negative x. Whereas on that last one, I replaced y with negative y at first and then multiplied the negative 1 through. Because I got to have y alone in the end. Is that making sense? Are you seeing what I'm saying on that? So if you just always think that way, whenever they flip something sideways or vertical, you just think that means replace x with negative x or y with negative y. That'll always work. That'll always work for you. That's what it truly means. And then you got to get normal y in the end, of course. Right? So I just replaced right here. I just replaced y with negative y, and then I had to multiply through to get it back to normal y. And that distributed the minus all the way across. And now here, I just replaced x with negative x. And there's nothing more to do. So there's our final equation. Does that make sense? That is the equation that would be moved down 3, reflected about the x, reflected about the y. Good? And they're going to ask us to do it backwards. Every which way. They want us to master this, which is good. It's a very valuable skill. So, all right, so now they're saying, all right, you got some point, 8, 1. It's on the original graph f of x. There's some kind of graph over 8, up 1. They're saying, some kind of graph, blah, blah, blah. And it goes through the point over 8, up 1. Well, that wasn't even a function the way I drew it. But anyway, whatever. We got some picture. I don't even know what the picture is. But there's a point 8, 1 on the original f of x graph, over 8 up 1. Now, what's going to happen? Where will that 0.81 travel to when you change to f of negative x? That's their question. So we're learning about how things move when you fiddle with their equations. So if you take the 0.81, this is bugging me. This function would fail the vertical line test. There we go. All right, so 8,1. So we got some point on some function. I don't have any idea what it looks like, but I know the point over 8 up 1 is a dot on the original graph f of x. And then, what if you change this to a new equation, f of negative x, where's the 0.81 going to go? Well, what does the negative on the x do? Just changes the x, doesn't it? Negative 8,1. Nothing too fancy yet, right? Just gonna switch the value on the x, right there. Just negative on the x. Good.
Negative x kind of is seen as y, right? Like when you're graphing it.
Well, yeah, the whole f is y. So that means plug in negative x. What is the y value?
Negative y, right? Like, isn't.
So this means plug negative x into the function. What it equals in terms of y, I just don't know. I don't have the whole function here.
Okay.
I can't really tell.
So-
All I know is they're saying plug negative in for x on that.
Because for the other problem, for step 2, you said replace y to negative y, and that changes the whole rest of the equation, right? Because, do you see what? Because
I do. Okay, the difference with that example,
Yeah.
good question, I'm with you. The difference for that example is the whole problem was about changing the whole equation. Here I'm just moving a point. So here I was changing the entire equation. Every step, they said, do this to the equation, do that to the other thing. On this one, I'm just moving a single point. I'm just saying, where does the 0.81 go? When you do this, it just changes the sign on the x. That's all that does. Let's try. So they're saying y equals negative 2 f of x. And the original point is negative 3,7. Where's he going to go when you do this? It was negative 3,7 on the original. Where's it going to go when you do that? So that negative 2, is he going to affect the x value or the y value? The y value. He's going to affect the y value. He's going to and it's multiplied, right? So it's going to multiply the y value by negative 2. It's going to be negative 14. That's all. Good on that? We're just seeing if it's an x effect or a y effect. So 15. All right, so basically they're giving me a couple points. Those are both x points, x-intercepts, right? And they're saying, hey, okay, they're on f of x. Now we're going to do stuff to it. So what did they do there? They added 4 to x. These are both x values. So should I add 4 to both those guys? Am I going too quick? So they're giving me these two x numbers. And they're saying, now do x plus 4. Should I add 4? You talk about my tone, no. Why not?
Because it's opposite.
Because x is the opposite. So plus 4 is actually going to go minus 4, which is how you got minus 13 and minus 10. The two answers there. Does that make sense? So whatever you do to x in a function, it has the opposite effect on the entire graph, which means all the points. You understand? We're just, another way to say what happens to a graph is to say what happens to all the points. Because that's what a graph is all the points, right? So we're just saying you got a couple of points, negative 9 and negative 6. What happens if we do f of x plus 4? Well, opposite. It subtracts 4 from both those points. What happens when we do x minus 8? Let's go down to here now. So x might go back to the original again. We're starting again with negative 9 and negative 6. How do I know I'm starting again? Well, because this is just f of x minus 8. It doesn't involve the x plus 4 anymore. It's not building upon because it's not using the x plus 4 anymore. It's just all brand new, x minus 8. So what's that minus 8 going to do? Plus 8. It's going to add it. Opposite, right? That'd be negative 1 and plus 2. That's what we got. All right, start again. Now, again, here we're not building. How do I know I'm not building? Because it doesn't say 5 f of x minus 8 or something. Right? It doesn't incorporate the previous thing at all. It just says 5 f of x. Just all brand new, just plain old f of x again, but now 5 f of x, okay? Is that 5, What's that going to, is that 5 an X effector or a Y effector? Y. So what's it going to do to these X values? Nothing. See, they're the same. They're testing if you're aware of that. No change on the X values. That's a Y effect. And what about this one? Just going to make them negative, right? Just going to make those, it'll just take the -9 and the -6 and make them +9 and +6. Good on all those?
Wait, that just makes it positive?
Right, because it's just a negative on the X values. Just it multiplies them by -1. Was it 19? You don't remember either, huh? Something like that. Here, I can go back. This is number 22. So number 22. So basically they're giving me this equation, 1 over 8x. They want me to say which of those graphs is this. This will be on the exam. So how do we do that? How do we take an equation and figure that out? Well, it's one of those. It's that kind of thing. How do we know which one? Well, yeah, that 8 is, yeah, I would just make a table, honestly. It's just hard, because that's a kind of compression expansion thing. That 8 is multiplying the x. X is opposite, so it's going to not stretch the x, it's going to compress the x. But that's hard to see. I would just make a table. I would just say, okay, look, x is 0. Let's plug into 1 over 8x. This is going to be 1 over 0, 8 times 0, which is just undefined. That means no, right? 0, no. It doesn't hit the x-axis. Okay, that's not a lot of information. Let's keep going. Let's plug in 1. When I make a table, I just plug in super easy numbers, like x is 0, x is 1, x is 2, maybe -1, you know, just some simple numbers. Whatever it takes until I can tell which option's right. Let's plug in 1. 1 over 8 times 1 be 1/8. So let me do a couple dots now. Or it's only one dot, huh? Over 1 up 1/8. It's barely up at all. Over 1 up 1/8. Okay. Let's, what if I did like -1? It's good to do a couple negatives. 1 over 8 times -1 be -1/8. So back 1 down just a tiny, tiny bit. Back 1 down 1/8. So, can you tell which graph it is?
B.
It's B, isn't it? It's this one here, right? Because it's not this one. This one's way over at 5 already, and you know it's not hugging tight down here, is it? The other two aren't even in the right quadrants. Is that good on that? So just make a table until you can tell. For compression, things are hard. Okay, y equals negative cube root. So you'll have in your 3x5 card that the cube root of x is the sideways snake, right? If you notice, the root graphs are always pretty flat, and the power graphs go up and down fast because they're powerful, right? You know what I mean? Like x to the third goes up and down fast. Goes through the origin there, right? And so does x squared, right? Up fast. Whereas the cube root and the square root, they're kind of flat. Because roots, numbers don't get big very fast when you root them. But when you power them, they get big and super negative fast, don't they? Right? You get that basic feel? The power graphs go up or down or both real quick. The root graphs mostly go sideways because the numbers don't get big with rooting. So you see the cube root go, oh, it's like that. Now what's that negative going to do? Is that negative an x or a y effect? It's a y. It's going to flip it, so it's going to go like this, isn't it? Flip it upside down. So it's what? D? Me good? All right, so there we go. So, all right, yeah, this is a little tricky. Minus x cubed plus 3. Yeah. So, the order of things matters on this one. Let me do this. Let's just make a table. I would make a table for sure on this one. Let's make a table, and then I'll show you why afterwards, because you might just think, oh, I can do it. It's just a flip, and it's an up 3, and there you go. And you're saying, it's D. You're right. It is D. But they could have made it more tricky. They could have made the result more tricky a certain way. How so? They could have made it... Yeah, they could have made it A. It's not A. Now, of course, you might be thinking, no way, mister, it's not A. That one's down 3. This is up 3. Yeah, you're right in this case, but they can be more subtle than this example because the flip can happen afterwards. In other words, if I take a graph, the normal x cubed graph, which normally goes like that, and I move it, let's say up 3 first. I first move it up 3 like that. First move it up 3. And then afterwards, I flip it. Remember, it doesn't just flip in place. It's a flip about this axis or the other axis. If I flip it about this axis, this will go down here. And the whole thing will go upside down. But if I flip it first, like if I just start with the original and first flip it and then move it, it'll stay like it was. You see the problem? The order matters. It's not just what happens, but what order it's done in. Have I lost you? Do you see all that? I'm trying to present the problem, then I'll show you the answer. The answer is mainly make a table. Right? So you understand? So the thing you got to get really clear in your mind is when we talk about these flips, everybody thinks, oh, just right where it stands, right there. No. No. The flip is about the axis. It's like I'm grabbing the barbecue shish kebab thing and I'm turning it at the axis, right? So in other words, that's what the flips are, right? They say about the x or about the y. So if you have a graph that's like up here or something, and you grab this axis and you turn it like a rotisserie, that's the word, like a rotisserie, right? You grab this axis and turn it. Where's this? This guy's not just going to flip standing in place, right? That's what you don't want to think. That's not a true thought. He's going to flip down here, won't he? Right? So if they're off the origin, when you flip them, the whole thing rotates. You understand? It's a flip about an axis, not a flip in place.
So is it always left from right? You translate.
There's a long story. I'll get there. But hold on. You understand the problem first off? It matters, right? What matters? The order. Because if you move it off the origin first and then rotate, it's going to end up down here. Even though you might have thought it was plus at first, and it is plus, it ended up negative, not because of the movement being negative, but the flip caused the positive movement to end up being a negative effect. See the trick? But if the flip comes first, you have some kind of thing, and you first flip it, right, originally, and I flipped the x cubed. That's what's been done on this one. That's why we're lucky it didn't do something weird. It's been flipped. Now, how do I know it's been flipped first? I'll show you, but hold on. If you first flip it, right, that's upside down, right? Normally the x cubed goes like this. So first flip it, then move it. Yeah, it's no big surprises. But if I first moved it up 3, it was like that at first, and then grabbed this like a rotisserie and flipped it, it would have come down here upside down. Right? You with me? So I just want to plan in your minds that it's not so simple. The order matters. So when you look at that, you go, no, that's just an up 3, flip it. Well, which one is it? Up 3, then flip, or flip, then up 3? Because that's the matter of this graph or that graph. Long story short, make tables. If you want, I don't know if I have time, I'll show you the why. Yeah, I can show you, because I've almost shown you with other things. How you know from the equation, it's pretty complex though, what order. But I would say, before I do that, just make a table. Make a table. Don't be overly confident in your ability to read the equation. Make a table. So I would just plug in 0. What do you get? Minus x cubed plus 3, minus 0 cubed plus 3, that's 3. Which one goes through over 0 up 3? This one, we're done. That's all you need, right? And he's upside down. I mean, I know it's not this one because that one never flipped. It's clearly flipped. We know this minus sign is going to flip the thing at some point. And this one's up 3. This one's down 3, so he's not the answer, although he is flipped. So that's how I know it's D, not A. Just by 1 point, I knew. It was D, not A. Everybody see? Because he's flipped, and he's up 3. This guy's not flipped. This guy's not flipped. And this guy is flipped, but he's in the wrong spot. So that's all you got to do is make a table. Just 1 point. Everybody see that? Do that. Now, why the order and all that? Look at the time. I'll just say it quick, and it's confusing. You want to talk more about it? I'd love to talk about it in my office hours with you. But here's the story. If you thought it is, in fact, a flip first, and then a move second. How do I know? Well, because if you take the equation x cubed and you first flip it vertically, what does that mean? Replace y with negative y, right? And then you got to multiply it through, so it becomes negative x cubed, right? That's good. Move second, move what? Up 3. So then you just take this and you add 3. And that's our equation. So it's a flip first, move second. Okay, yeah, but why, Mr. Heron, isn't it the other way? Watch if you tried and thought it was the other way. It's not true. If you take y equals x cubed and you first move it up 3, then you'd go x cubed plus 3. Looks good so far. What's the problem? And second, flip it. Let's replace y with negative y. And then multiply both sides by negative 1. Negative x cubed minus 3. See, first move, second flip would be that. Different equation. That's hard. Make the table. We got 1 minute. Got